Good morning, students. Can you hear me? Hello.
Morning, sir.
Good morning. Thank you for confirming me. Let's start. In the last class, what we have seen is we have seen uh, conduction. Okay. We have concluded our discussion on conduction. What we have seen in that is, especially we started at specific heat. We have seen the difference between the CP and K, that is a specific heat and thermal conductivity. The major takeaway is this part. It is CP is ability to store heat and K is ability to conduct heat or transport heat. So this is the major difference between your CP and K that we have seen. And then we have seen what is thermal diffusivity also and its definition, what is its formula, what is its unit. This is what we have seen, and we have solved a problem, okay, based on a conduction principles, how it can be applied to a real-time case, and you can solve what will be the rate or the cost of heat loss that will happen when it comes to a electrically heated home. Okay, this is what we have seen in the last class. Now we will move on to the convection. Okay, I already told you that there are three basic modes of heat transfer. They are conduction, convection, and radiation. And in each part, we should see three again. So let's start convection today. Convection. Okay. In convection, we shall see three things. The first thing is governing law. What is the governing law we have to see? And the next thing is physical mechanism of heat transfer. Okay, this part, these three things I told you already during your conduction also. For every mode of heat transfer, you have to see these three. Okay, mathematical expression. These three things you should have. So coming to convection, what is the governing law? Actually, this governing law you must have studied in your mathematics course. It is actually Newton's Newton's law of cooling. Newton's law of Newton's law of cooling. Okay. So what is the physical mechanism of heat transfer? The physical mechanism of heat transfer is molecular diffusion and molecular collision. Somebody switched on their mic. Nitish Reddy, kindly switch off your mic. It is having some disturbance for me. Okay. So the physical mechanism of heat transfer is molecular diffusion and molecular collision. And the mathematical expression we have to see here. The mathematical expression is Q is equal to H into A into delta T. Okay. So this is the basic story of convection which you have to remember. Okay. Let's keep this aside and let me ask a question. Okay. See, one day morning, what happened is I usually used to drink milk at that point of time, and my mother used to give it in a cup of coffee. On that particular day, what happened is my mother, she was giving, but I was rushing to college. I have to come fast. The time is out. So when I was coming very fast, I said, I don't drink. It is very hot. Okay, if it is hot, I cannot drink. Then what she did is she poured that milk into a plate. Okay, now it will not be that hot. You drink it. Interestingly, it was not hot, and I drank it, and okay, okay. So this is what happened. So why did that happen?
More surface area.
more surface area. Okay, that is the reason why with a cup of coffee they'll be giving you a saucer also. Okay, so that you will pour this in that saucer and then drink it. So this part is actually your convection. What Newton's law of cooling says is Q is proportional to area. More is the surface area, more is the heat transfer by convection. And Q is also proportional to the delta T. Okay. When I say delta T here, if I have saucer in my hand, there is a fluid. This fluid is having um, more delta T. That meaning uh, the fluid is, let us say, having a temperature of fixed temperature of let us say 50 degrees centigrade, and the atmosphere is at 25 degrees centigrade. Okay, that is one case. Okay, let us take two cases here. Temperature of fluid and temperature of atmosphere. The temperature of the fluid is 50 degrees centigrade. This is also 50 degrees centigrade. In this case, the atmosphere is at 25 degrees centigrade, and the atmosphere here is 50 degrees centigrade. In these two cases, which one will be a faster cooling? This one will be a faster cooling. Why? Because the atmosphere is already cold out there, the heat transfer will also be more. It is as simple as this. If you leave this pen from very higher height, it will go down at a faster rate. Same is the case with your temperature also. If the delta T is increasing hugely, so will be your heat transfer by convection. So the heat transfer by convection is depending hugely on your delta T. So that is TF minus T atmosphere. So here TM minus T atmosphere values has an influence. So this equation, if I take and introduce this a proportionality constant H here, I will get this mathematical expression. Okay. So that's how you got this mathematical expression from your Newton's law of cooling. Newton's law of cooling is the governing law here. This is the mathematical expression. How did you get this mathematical expression? Using this discussion, using this principle, you got it. Okay. Coming to the physical mechanism of heat transfer. Physical mechanism of heat transfer is molecular diffusion and molecular collision. Like in the case of fluids for your conduction, same is the story here. Okay. So each molecule, if you take a space here, okay, if you take a space here, in this space, there is a fluid flowing. When the fluid is flowing from each particle, the energy is transmitted to the other one. Each particle, the energy is transmitted to the other one. Each particle, the energy is transmitted to the other one. So this is the way the energy is transmitted. So what is happening is molecules are diffusing one into the other, one into the other, one into the other, like that. So in the process, the heat is actually transferred. This we call it as molecular diffusion, or they may collide with each other. That you call it as molecular collision. Okay, let us see this with one more example. Okay, you take a vessel, and this vessel you are trying to heat it from the bottom. It is filled with cold water, and you are heating it from the bottom. So, if this is the case, what happens to your what happens to your uh, fluid movement here? If you look at this case now, the fluid movement is happening actually in this way. It will get heated up first. The one at the bottom will get heated up first, and it will go into the top. Okay, and then one at the top is cold actually. Because it is cold, it will try to come down. That is, high density particles will come down and the low density particles will try to go up. So this is a hot molecule that is going up and the cold molecule is coming down. The process where the hot molecules go up and cold molecules come down is called as your convection current. Okay, this is nothing but the convection happening. So what is very important thing when it comes to your convection is fluid flow heat transfer. It is fluid flow heat transfer. If there is a fluid flow, there will be convection definitely. Okay. If there is no fluid flow, maybe a conduction case. But if there is a fluid flow, it is a convection case. So convection is fluid flow heat transfer. Convection, instead of saying convection, you can simply say that it is a fluid flow heat transfer. So remember this word, convection is fluid flow. There will be bulk fluid motion. In any case, if there is a fluid motion, you can call it as a convection case. It is as simple as that. Okay. So that is a part regarding your physical mechanism of heat transfer. Okay. Now let us look at the mathematical expression. So the mathematical expression, I already told you that Q is equal to H into A into delta T. So this is your equation. When I say Q here, okay, here it is a rate of heat transfer by convection. Okay, some textbooks write convection here. Whether I write it or not, you have to write it is by convection only. We are speaking about in convection, so it will be convection thing only. Some textbooks have dot here. When there is a dot here, they represent that it is a rate. Okay, whether or not you have dot, it will be a rate. Why it will be a rate? Because you are mentioning it in watts, which is nothing but joule per second. When you mention it in joule per second, no, it will be obviously watt. Okay. So don't get so much obsessed with the nomenclature. What I request each of you is don't try to remember the things, remember the mathematical expressions with respect to its nomenclature. Okay. Nomenclature is not important to us. What is important to is units. Okay. Remember the given formula with respect to units. Okay, if you remember the formula with respect to unit, you will not commit a mistake. If you remember with respect to the nomenclature, some people will remember that there should be Q dot. If Q dot is not given, it is simply Q. Simply Q means joule, like that some people will think. Okay, that is not right way of thinking. Okay, so what you have to look at is what is mentioned there. Okay, what is the unit of that Q matters to us, not the nomenclature with which it is written. Okay, kindly keep this in mind. Coming to next thing, A. Area here is area with which fluid is interacting. Area with which the fluid is interacting. Fluid is interacting. It is meter square. And the delta T. Delta T is temperature difference between your solid and fluid. It is the temperature difference between solid and fluid. Then H is there here. H is your proportionality constant. We call it heat transfer coefficient. It is heat transfer coefficient. Can somebody write the units of this one? Can somebody tell the units for this one? What is the unit of heat transfer coefficient? You have it as watt here. Here it is meter square. Delta T is Kelvin or degree centigrade. Both are same. So what will be the unit here? This will be using this. You can write like watt per meter square Kelvin, which is actually Q by A into delta T. Q unit is watt, A unit is meter square, delta T unit is Kelvin. So the unit for this one is watt per meter square Kelvin. Okay, this is the thing regarding your mathematical expression, and each expression you have to remember how you take it up. Okay, now let me show the same expression with an example. Let us take a rod here. There is a rod, and this rod is at 100 degrees centigrade. The rod temperature, let me take it like TS, is 100 degrees, 100 degrees centigrade. And the atmosphere temperature. Atmosphere temperature means what? It is a fluid around, the fluid with which the solid is interacting. Okay, this is equal to 15 or 20, you can say, whatever the atmosphere temperature it is there. Okay. So you will take this thing and then you will have so and so area for this one. Yes. Okay. So when I take area here, whether you will take this area or this area, the whole area is a matter for us here. Okay. Let me draw this even more clearly. This is the rod. Okay. It has so much distance. So this area you have to consider, and this area you have to consider. The whole area you have to consider because when the rod is there in the atmosphere, no, this whole area will be interacting with the fluid, okay, with the atmospheric air. So this area you have to consider, this area you have to consider, everything you have to consider. But if this area is very small compared to this area, you may neglect this, that is okay. But in general, whatever the area you take here, it is area with which the fluid is interacting. That is very important thing here. That is the story of area. When it comes to delta T, the delta T, you have to take it in terms of the fluid temperature and the solid temperature. Temperature of solid minus temperature of fluid. Okay, this can also be written like Ts minus T atmosphere. Okay, so anyway, you have to understand what is that delta T. That is important. So the delta T will be equal to Ts minus T atmosphere. So your Q can be written like H into A into Ts minus T atmosphere. So this is the expressed in same way, a bit different way. The delta T is bit differently written here. Next, coming to the story of H. What is H here? H, I already told you that it is heat transfer coefficient. Okay, it is heat transfer coefficient, and the unit for this H is watt per meter square Kelvin. For your thermal conductivity, it is watt per meter Kelvin. It is heat transfer coefficient here. So this is watt per meter square Kelvin. This is also equal to watt per meter square degree centigrade. Why? Because the delta T is same in Kelvin and degree centigrade because plus 273 and minus 273 will cancel. Okay. So this thing you have to remember. Why I'm repeating it again here? I told you while I'm telling it for your what do you call conduction case also. Watt per meter Kelvin, watt per meter degree centigrade, both are equal. Okay, many people confuse with this. Okay, if the question is given in degree centigrade, they try to add plus 273 Kelvin minus 273 something like that. They do, and they confuse a lot, and they can't arrive at the solution. Both are equal actually. This should be remembered very clearly. Okay, and one more important thing regarding your heat transfer coefficient H is it is not a material property. It is not a property like thermal conductivity. If you take thermal conductivity, you know, every body will have a value of thermal conductivity. H is not like that. Okay. H, how you are getting this H? H is a combination of your solid that you have here and the atmosphere, the solid and the atmosphere. So when you take the delta T in your conduction case, no, the delta T there is actually for the same solid. Okay, let me write it here. Q, if I write for conduction, no, whatever the Ka T1 minus T2 by X you are taking, no, this part is for same solid. It is not between the solid and fluid for your conduction. It is for same solid. But whereas here it is between solid and atmosphere. So what happens is this H is dependent on combination of Ts and T atmosphere. So For a given combination of T solid and T atmosphere, you will have H. And H is also dependent on viscosity, viscosity of the fluid, density of the fluid, okay, the temperature, as I have told you already here in this case. Like this, so many parameters, so many physical parameters will be influencing the value of H. So H cannot be a constant. H is not a constant value for any given combination. Okay, for a given combination of solid and fluid, this will be keep varying. Okay, so keep this in mind. So this is a story regarding your H. That is, heat transfer coefficient is not a property like thermal conductivity. Heat transfer coefficient is dependent on combination of temperature of the solid and temperature of the atmosphere. Atmosphere, or it can be a fluid. Okay, when I say atmosphere, it is nothing but fluid with which it is interacting. Okay, H is dependent on viscosity, density, temperature of the fluid. H is not a constant value for any given combination. Okay, let us take this example itself. Okay, here you can have so many temperatures, here you can have so many temperatures. For so many combinations will be there. Based on these combination, this H value is highly varying. It is not like your thermal conductivity, so and so value at so and so temperature for a given material. It is not like that. H is not like your thermal conductivity. Okay, keep this in mind. Okay. So, moving on, let us solve a simple problem based on this convection case. What is that? So you can see this problem, right? Now, here, what is this problem is saying is, if you are writing a notes, please take a snapshot of this one, maybe in your laptop or in your computer. Take a snapshot and save this, so that when you are writing notes, you can leave some space for writing this question later on, and then you can move on to solving your question with me, along with me. Later, after the class, you can update your notes, okay, the space that you have left. Now, here in this convection case, what I'm doing is I'm taking this problem to understand this. So it is a 2 meter long and zero point 0.3 diameter electrical wire. So let us take this. See, it is 2 meter long and zero point 0.3 centimeter diameter, means it's very long and the diameter is very small. So the thing, the wire I'm taking here, and this wire is 2 meter long, and the diameter is zero point 0.3 centimeters, which is very less actually compared to your 2 meters. And here he has given that the room is at 15 degrees centigrade. So from this, you can write that T atmosphere is 15 degrees centigrade. And then the surface temperature, heat is generated in wire as a result of resistance heating. So this particular wire is it is connected to the terminals. Power supply is given, so there will be resistance for this one. Because of that resistance, the room is getting heated. Okay, and that room is at 15 degrees centigrade. And the surface temperature of the wire is measured to be 152 degrees centigrade. The surface temperature of this one is 152 degrees centigrade. So in steady operation, that is meaning, is meaning the steady state. With time, the temperature is not changing. Okay, when I take temperature as a function of time, so the temperature is not changing with time. So that's what is the meaning of the steady operation. Also, the voltage drop and the electric current through the wire are measured to be 60 volt and 1.5 amps. So the voltage is given as 60 volts and current I is given as 1.5 amps. This is given in question. Disregarding any heat transfer by radiation. Anyways, radiation we will not consider now. Determine the convection heat transfer coefficient for heat transfer between the outer surface of the wire and air in the room. So what he is asking you to find is H. What is the value of heat transfer coefficient? So the value of the heat transfer coefficient will be measured in so many watt per meter square Kelvin. So you have to get this value here. So it's simple question actually. Q is equal to HA delta T is your expression. I can say it like Ts minus T infinity, sometimes they write, okay? T infinity meaning temperature of the atmosphere around it, temperature of the surroundings around, okay? T infinity, I am writing it for now. Infinity meaning the atmosphere, okay? Most of the times this convention is followed in your data book also. That's why I'll follow T infinity from now on. So this is your T, yes. Now, what is your Q? Q is nothing but V into I. So Q, if I have to take this V into I. So here I'll write 60 into 1.5 is equal to H into the area. When I take area here, it is not pi by 4 d square. Okay, it is whole area. When I take the whole area, what is the formula? Pi dl. Okay, you will have two areas here. When I take this pen, you will get the video here. When you take this pen, you will have this surface area. Okay, this whole surface area is there, and then this cross sectional area is also there. So among these two, which will you consider here? You have to consider this part and this part also here. But I'm neglecting the diameter part. If you want to neglect, you can neglect. If you don't want to neglect, you can take it. It is pi by 4 d square two times on this side and this side. Okay. Even if you take it, you will get the same value. If you don't take it also, you will get the same value because this is 2 meter long and the diameter is very small. Okay. It's up to you to take. Okay. If you take it, the difference will be very small. The TS value is 152 and the T infinity value is 15 degrees centigrade. Now, uh, here this side is 60 into 1.5 as it is you put, H is unknown here. In this pi, you take it out. D value is given as how many? 0.3 centimeters. So 0.3 into 10 to the power of minus 2 I have to take because I have to take everything in terms of meters only, that is SI units. L is 2 meters given. So this is one thing. And then if I take pi aside, it is 1 by 2 into 0.3 into 10 to the power of minus 2 whole square into 152 minus 15. This is your equation. H is unknown in this expression. Somebody please calculate the H value and please tell me it is watt per meter square Kelvin. Please tell me that value. So please tell me what is this H value? Somebody please calculate and tell me. Rahul Kumar is saying that it is 32.48. Let me check it. So yeah, around it is 32 or 33. Okay. You can see in heat transfer calculations, you cannot get the exact value. Okay, the value will be little bit varying, especially this kind of thing is okay. But when you move to the complex equations that you have in the next units, as there you cannot have exact expressions. Okay? Here the value is around 33 watt per meter square Kelvin. Okay? This much uh, heat transfer coefficient you can get here. Okay. So is it clear in at least level? You have any doubts? Please ask me, or I'll move on to the radiation, the convection thing. If you have any doubts, please ask me. You can unmute yourself and please ask. No questions? Okay. Let's move on and you can go to radiation directly. But what I will do is I will give you a comparative overview between your conduction and convection. Okay, this comparative overview generally you don't have it in textbooks. I give it to students so that they will know the difference between the mathematical expressions that they have in conduction and convection. Okay, so here on this side, let me take conduction. On the other side, I'll take convection. Right? This side, I'll take conduction. Convection. Here, what is the mathematical expression? Q is equal to minus Ka dt by dx. Here, Q is equal to H into A into dt or delta T or Ts minus T infinity, whatever. You can take this side. Okay. When I say Q here, it is heat transfer rate by conduction. Here, when I take Q, it is heat transfer rate by convection. And then here, this is very important thing that you should remember. Area is the thing most of the students confuse. Area on conduction side is area perpendicular, area perpendicular to a direction of heat transfer. Whereas here, the area is area with which fluid is interacting. On this side, area perpendicular to the direction of heat transfer. Convection side, area with which fluid is interacting. Here also we write A, here also we write A. But areas are completely different. Here also you write Q, here also you write Q. But here it is conduction, here it is convection. This difference you must understand as we go ahead. Okay. The next thing is here delta T. Okay, even delta T people confuse a lot. DT, if I take here, temperature difference between 2 points in one solid. In one solid, you have 2 points. There you will apply this temperature difference. Here, the delta T is temperature difference between solid and fluid. Okay, this is a major difference between your delta T. And then your proportionality constant, here the unit is watt per meter Kelvin. Here it is watt per meter square Kelvin. This is the thing. If I have to represent this particular thing on a diagram here, you will take a wall here. Let us take a wall. This is your wall. And then here you have temperature T1. Here you have temperature T2. The temperature dropping like this. And this will be your dx. And this area you will consider. Okay. So this is the area perpendicular to direction of heat transfer. Whereas on this side, you have a rod here. You will have a rod, or it can be a solid surface. It can be anything. Any solid you can take on this side. This will be a Ts, and the T infinity that is in the atmosphere, and the area is the whole area. This area you have to take this area. The complete area will come into your area. So that is a major difference between these two. So this thing is very important. Many people confuse between these two: area, H, K, delta D, delta T. So this is the thing. At this level, you have any question? Any questions you have?
Sir,
Yeah, please ask.
sir, how to find H in real life, sir? We don't find
H in
coefficient of,
real life.
yeah. We generally
Yeah.
we don't
How
know
to
the
find?
heat. So
Hmm.
without knowing that,
This
how
is
to,
how you find H in real life. This is a real-time example that I have told you here.
but
Can you
there
measure
won't,
temperature?
sir.
Yeah, listen. Can you measure the temperatures? Yes, you can measure the temperatures using thermocouples.
Yeah.
Okay. And can you measure the voltage and the what do you call current? You can measure
Mhm.
using voltmeter and ammeter. You can measure. Okay.
Mm.
Area you can measure. Definitely area you can measure. Once you can measure all the remaining things, H you will get. It is
This
as
is
simple
only
as that.
for wire, no, sir. Generally, we
Huh?
don't get Q. For wire, we have formula, sir. For normally
Hmm.
solid part, how to find Q, sir?
Hmm.
It will be
Hmm.
difficult.
That
We
will
have
be
to use,
difficult.
sir,
Hmm. Hmm.
on what
Yeah.
parameter
That
we.
part, that part we will see in unit 3, but I will tell you a simple thing here. Okay. Nu is equal to 0.023 into Re power zero point 0.8 into Prandtl power 0.3. See, what you are seeing here is a numerical correlation. This is a Nusselt number on this side. Here you have a Reynolds number. Here you have a Prandtl number. So for finding this H value, as I said, it's a very complex thing. That is the reason why people have gone for the non-dimensionalization. Nusselt number, Reynolds number, Prandtl number are actually non-dimensional parameters. Using these non-dimensional parameters, you will find H. Nu is non-dimensional H. This H into D by K. This is a formula for Nusselt number. So you have H here, right?
Mm.
So D K is anyways known to you. Is anyways known to you. Why K is known to you? You know the material. You know the material, the thermal conductivity. You can
Thermal
thermal
conductor.
conductivity anyways is there. Reynolds number formula. Can you tell me? Rho
Mm.
VD by mu. Okay. So velocity you can calculate. Dynamic viscosity you can have. Diameter you can have. Uh, Density you can have. Okay. And Prandtl number mu Cp by K. This is it.
Mm.
So it is a dynamic viscosity. It is storage capacity. So except H in this equation, you know everything.
Mm,
Okay.
yes.
You can find these data from your data. I told you that there is a data book, right?
Yes. Yes.
Okay. You will use this Keep and mass transfer data book. You can find it. So this is one example I have shown. Okay. In real time, we will have so many cases. For one particular case, this is valid. So based on given case, you have to select given numerical correlation and then find H. This is the way you find it. You got it? Is my question answered?
Yes, sir, yes.